Hello and welcome to day 3 of the Krypton Cougars programming workshop. Today we're going to be going over aiming with Limelight. So this is day 3 out of 6. Already said we're aiming with Limelight. The last time we went over Tank Drive. The day before that we went over Java motors, sensors, and controllers. So if you're not familiar with that stuff yet, it would be a good time to go and look at our previous workshop days before watching this video. So if you're here presently, you can join the Menti, but we're just gonna continue with that for now. So today we're going to be aiming with Limelights, but one important component of just kind of aiming in general, or really telling your robot not to go a certain speed, but to go to a position, is using something called PID. And you see a little F here in parentheses, which stands for feed forward. So PID plus feed forward. So basically, you can use PID to kind of adjust output, right? So in our case, if we have our tank drive turning, the voltage to your motors, to adjust output based on the difference between the desired set point and the current measurement. In other words, the difference between where we want to go and where we are. This allows for precise control over robot movements, including velocity or position. So PID stands for proportional, integral, derivative, and then feed forward. And we'll explain each of these terms real quick. Basically, proportional multiplies the error. And if you see this word error, that basically means how far away from your goal you are, right? So if we want to be straight, but we're 30 degrees to the left, your error would be 30 degrees. Basically, you multiply your error by Kp. And Kp is just a number we choose. It's like a variable. So for example, if you were 10 degrees off and your Kp was 0.01, you would go at 10% speed, because 10 times 0.01 is 10%. If you have too large of a value for this, it leads to oscillations, kind of as you can see over here. And this should be doing most of the work in your PID controller. And I think it's somewhat intuitive how this kind of works. Basically, if you're off way too far to the left, right, you're off by a lot, you multiply by Kp, and it tells you you need to go to the right with a large voltage of a lot. But if you're really, really close, that voltage is going to be much less because you don't need to go as far. You probably shouldn't be going as fast. So integral is based on the total error. This helps you reach the target if P undershoots. So in this bottom right graph, basically what's happening is we are applying a voltage that is proportional to the distance, but in some cases, you're still going to have a little extra resistance that keeps you from getting all the way there just using proportional feedback. For example, if you had an arm in robotics and you just wanted to use PID to control that, if you only used P, eventually the weight of the arm would be counteracting all the proportional response. And basically you have your error, that multiplied by Kp would cancel out to the weight of the arm, but you still need to have some error there for you to kind of get that feedback. So you'd settle a bit below your set point. Having an integral value kind of allows you to see, oh, look, a certain amount of error for a long time. It kind of adds up all the error over time, and it allows you to correct for that. So this would be an example of, I guess, having too much integral, but as you can see, we still reach our set point eventually. And then derivative is based on the current rate of change, and it helps to dampen the control and basically reduce oscillations. If we go back a bit, you see this robot right here, it has its P too high, and it kind of keeps wiggling. What D does is it helps to reduce those oscillations by basically working in the opposite direction of the direction the robot's moving. So if it tries kind of getting too fast when it's turning, D will work in the opposite direction as a dampening force. And feed forward is a final thing. It's not necessary in all cases, but it is very useful for helping your PID function better. Basically, feed forward is kind of just adding a voltage or any other form of output to your like motor output when you're before you calculate your PID based on where you want it to be. So if you had a certain angle that your arm was at, right, you would be able to calculate how much voltage you would need to maintain that angle, and that would be your feed forward. And then you could add PID on top of that. That kind of helps deal with this not quite reaching the set point because of the weight of the arm without doing an integral. So ideally, feed forward can replace most of your I term. Any questions? I see we had 2 people join, so. Sorry if you're speaking. I'm trying to see if my volume's on. I'm not sure it's on right now. Okay. I think it's on, but. Okay, so we're going to be moving on in a second. But so the mathematics behind PID, and I'm not sure if you can quite see on the screen. I think the image is a bit oversaturated, at least on my camera. But if you know calculus, this is kind of helpful. Pretty much what it's saying is that we have our input, right, where we want to go. And we're also taking where we are and we're finding the difference between them. And that's our error. And then we see how far away we are based on error. We integrate our error over time, basically add up our error over time, and then take the derivative of it, basically see how fast we're moving, how fast our error is changing, add those all up, and that is our output. It's just the mathematical phrasing of what we just went over with PI and D. We don't really use calculus for the PID math. We just use some helper classes and methods in WPILib at least. So here's the Menti question code if you want to use that. I believe it's linked in the chat, but so one question we have is why do we use PID for aiming? And basically, if we're aiming, right, we don't want to be telling the robot what voltage to go at, but basically what position to go to. So we have a target that we can see with our camera, and we know if it's to the left or to the right of the robot. And what we're going to do with that is probably just have a P term. So if our error, we can calculate our error based on how far it is from the cursor, but you can use that error with a PID controller to kind of get that error down to 0 and have your target be where, like kind of in the center where your robot's aiming. So when we on our team do vision, usually we're using a limelight. Now there's a few other options. Specifically, photon vision is very popular. It's a lot like a limelight, but open source, and you can kind of run it on any coprocessor you want. So it can be cheaper. There's a bit more flexibility there. But limelights are a lot, I guess, easier to set up. Not a lot. They're easier to set up by comparison, but photon vision is making a lot of progress in that area. Additionally, you can get a like IP camera and hook that up and process it directly on the RoboRio. But RoboRios currently are a bit slow, so we don't use that as it can take some time and give you less optimal results than using a coprocessor like a Limelight or a Raspberry Pi running Photon Vision. And when we say coprocessor, we just mean some sort of processor that isn't the RoboRio. And usually you'll communicate with that via network tables. So, or a library that is provided, like in this case. But a Limelight in general, originally, right, was pretty much a camera, as you can see right here in the center, with some lights attached to it. And the idea is that it's an FRC smart camera that allows robots to see. And it uses LEDs to bounce lime-colored light, so green light, off of retroreflective targets, which basically, if you have a retroreflective target, your light goes in, and then it bounces directly back at where it came from. So if you have light coming off of these LEDs, bouncing off a retroreflective target, right, it would go boom, and then it would bounce right back to the camera, and it would be able to very, very clearly see where those retroreflective targets are. That kind of tape has actually been phased out in FRC usage by now. 2 years ago was the last time that it was actually used. And this year there was no FRC tape. Sorry, not FRC tape. No retroreflective tape used. Instead, April tags have been used. So Limelights and a lot of other cameras can detect certain patterns called April tags and deduce their position relative to them. So these April tags, they look like this. Usually you'll see them taped to the wall of the FRC arena in different spots depending on the game, but they pretty much always look like this, like a little mini QR code. And they're used in all modern FRC games instead of retroreflective tape. Some of the benefits of these, you don't need a light on your robot blinding people and or shining light at other robots. So you can just use any normal camera and it should be able to pick up on these. Additionally, you can specifically deduce your position relative to them in 3D space, which is an advantage over just simple retroreflective tape, where you can kind of only get the X and Y coordinate of that piece of tape relative to your camera. So this is an example of a robot aiming and shooting with a Limelight. You can kind of see the green glow coming from the robot before it shoots, and it's looking at the retroreflective tape. So for tuning a Limelight pipeline, we're going to go over this in the lab. So I won't spend too much time on this. You can always look back at this presentation. But you're going to hook your Limelight up to your robot via Ethernet and power. And then you should, once you connect to the robot, you should be able to access the web interface at http://10, and then your team number with like a dot in the middle, .11, and then this port, 5801.
Limelight.io for a fresh one. It's Limelight.io.
Okay, Limelight.io should also work.
Limelight.local.
Limelight.local should work for a fresh Limelight as well. So if you don't already have it set up, this is the ideal way to do it, but Limelight.local works as well. So for example, if our team number was 2539, which it is, this would be 10.25.39.11. If your team number was 12,345, it would be 10.123.45.11. And if your team number was like 103, it would be 10.1.03.11. And this is the same beginning IP address as your RoboRio and radio. So these are the instructions for tuning a Limelight pipeline for retroreflective in case you want to look back on this and see how to do that. We're not going to go over that as retroreflective isn't really used anymore. And we actually don't have any retroreflective tape anymore. This is an instruction guide on tuning a Limelight pipeline for April tags. Basically, the main things are you want to set your pipeline type to fiducial markers. You want to use the highest available resolution if you're doing 3D tracking. If you're not doing 3D tracking, you don't have to go with the highest resolution because sometimes going for lower resolutions gives you faster frame rates. You want to set your black level low your gain level to 15. And then you kind of also want your exposure to be as low as possible, but only until your camera kind of stops being able to see able tags. And you also want to choose these settings. We'll go over this when we do the lab, but for us, in our case, we're going to be aiming at possibly 1 and 2. We'll see when we actually get our April tags. And this is just the Limelight official guide for doing this. So programming-wise, getting Limelight values from network tables has been made pretty simple in more recent times by this Limelight helpers class. This is a library provided by Limelight. It's not like the other libraries we've used so far. This one is literally just a file that you copy and paste into your robot code. So it makes it really easy to make modifications to it if you want, and it's pretty easy to install. So basically, we're choosing a Limelight name of Limelight, and I'm just separating this out into a variable to make it clearer. If your Limelight name is always the same, you could just put it here, but I would recommend separating out in case one day you do change your Limelight name. To get TX, which is basically how far your target is from the center of your camera, on the X coordinate side to side, you do Limelight helpers.getTX and then your Limelight name. And to get how high it is, you just do .getTY. And there's plenty of methods like this for getting other target related items. So commands are something that we're going to use. They basically, to make this aim at target command, which eventually we're going to run on the robot, but they're kind of actions that the robot performs. So for example, here they're on the right, move to scoring position is an action that the robot performs. It has a start, a middle, and an end kind of. That middle kind of going on for every instant that is not the beginning or the end. Stow wrist, for example, that would have a beginning, a middle, and an end. The middle probably being a PID control loop telling the motor what speed to go at to get the wrist to the right position. And then the end basically telling the motor to stop because it's in the right position. They encapsulate logic, which is required to run a command. So pretty much they have their logic for what to do at the start, what to do while the command's running, what to do at the end, and also logic for whether or not the command should end yet. And they interact with subsystems to get sensor values or drive motors. So this is a command class, right? Previously, in our code, we did make commands. So this, for example, is an example of a command, but this is using the command factory, it's called. Basically, the command factory is a way to use methods to create commands without creating new classes. So this is our arcade drive command, and we never made a new class for this. We just used methods to create it. But previously, before the command factory was available, the way you would create all your commands would be like this. You'd make a new class. So here we have public class command extends command base. And this basically has a constructor like any class, and then these 4 methods. Initialize is called exactly once when a command starts. Execute is called periodically while the command is running, specifically every 0.02 seconds on most robots. End is called when the robot code finishes running the command. Is finished is basically called every 0.02 seconds, and it's pretty much asking, is the command ready to finish or not? And this should just return a Boolean. True if the command is finished, false if it's not. And we'll go over how to create this with our aiming command. So an approach to aiming using a Limelight is to create a PID controller class and set the desired angle we want to go to 0. Then turn the robot towards 0 from the Limelight with the TX value using PID. That PID controller ideally is going to try to make that TX value closer to 0. And when your TX value is 0, then you know you're aimed at the target because your target's in the center. So it kind of just works out. And then we want the command to finish when the angle is within tolerance. So for example, our tolerance is going to be around 3 to 4 degrees. But you can tune for less or more depending on your use case. So if you're following along, you're going to need to install Limelight lib. And this is just that single file I was talking about. So your options are go to docs.limelightvision.io/this, basically this option A. And I'm just going to do this quickly to show you how you would do it. You then go down to usage, click on this if you're using Java, which you should be if you're following this tutorial. And then press on that, and it should download it for you. And you're just going to want to basically drag this file into your VS Code. So we're going to open this in files. And you see right here where it says robot, you just want to drag this right over there. Yes?
Connection.
Oh. Okay, 1 second. We're having a slight technical difficulty. Okay, sorry about that. We just had our screen back here disconnect, so the people following along at the build site weren't able to view for a second. But basically, yeah, you're going to want to go here, click on this link or this link. They're both the same. Click on releases, Limelight helpers. That automatically downloads it. Then you're going to want to open it in either Finder or File Explorer, whatever you're using. And you're just going to want to drag it over into Robot. And we already have it in there because I just dragged it in. But Limelight helpers. And the inside of it should look a little like this. Limelight helpers v1.9. And then you're just going to have a ton of methods, right? Don't mess with it too much. Does anyone have any questions? Okay, in that case, we're going to continue. If I can find our presentation again. So option B, this link just directly downloads it, but it might be outdated in future versions of the presentation. So to aim towards a target, this is going to be our command example. And basically, you're going to want to create a command by making a new class and extending command. And for these fields, right, this is kind of everything at once. We'll go through it a bit more detailed in the lab. You're going to want to create a drive subsystem, or really any other subsystem you'd need for controlling it, a PID controller, and we're just saving our Limelight name as a constant. And we also have target ID here. Now you need a constructor for your command. Our constructor, all it's going to do is take in the drive subsystem. This is something known as dependency injection. And basically it means the aim at Limelight command needs to run some things on drive subsystem. It needs to call some of those methods. So we're going to pass the drive subsystem in as a parameter for the command, and it's kind of just going to save it. Then we're also going to create a new PID controller, which you need to import. And we're going to set KP to be 0.1, KI to be 0, and KD to be 0. In case you're following along in code, I'd like to point out that these little KP and then colon, or position tolerance and then colon, it's kind of hard to see, but it does have a little gray highlight box over it, and it's also gray itself. This specifically, when you see it in a method, is just a kind of like syntax highlighting. It's not actually in the code. Don't write it out. You'll get an error. Really, all that's written here is parenthesis to end parenthesis. So it just kind of helps you know what specifically you are passing into the method, what it actually does, without having to mouse over the method. So then we add requirements. This add requirements thing tells the robot code what subsystems this command needs to run. And this helps prevent your robot from trying to run two commands that require the same subsystem at the same time. In our case, when we run this command, it's going to stop the default command because the default command also needs the drive subsystem. So next, we're going to have our initialize method, and we're just using this @override syntax here to let the Java compiler know that we are purposefully overriding a child method, a super method. Basically, command has an initialize method already created, but we're overriding it. So mpid controller.reset, basically we're just telling the PID controller to ignore any previous information it was kind of picking up on. Because we're starting the command fresh, we don't want to kind of have old memory stuck in it. And then for public void execute, right, this runs every 0.02 seconds while the command's running. This right here gets the fiducial ID. So if we have an April tag, we have one back there. That's an April tag, and its ID is 8. We're going to be aiming to that hopefully today. But if our fiducial ID from our Limelight is -1, aka our Limelight doesn't see an April tag, if your Limelight doesn't see an April tag, it'll tell you -1. Then we're going to set our drive speeds to 0 and 0. Otherwise, we're going to calculate our distance horizontally from the April tag, and we're going to put that into our drive subsystem, specifically with one side as more than the other, or one side being the opposite of the other, because that'll allow us to turn. And then finally, we have end, which mDrive subsystem dot set drive speeds, left %0, right %0. It just tells the robot to stop turning. And is finished, it returns if our PID controller is at the set point, aka if our robot has turned to within the tolerance of the command. Does anyone have any questions? So that's it for the lecture section today. So we should be moving on to the lab section now. We're just going to kind of be recreating that command, but step by step, working off of the code that we made on stream last week. So if you're following along, now's a good time to open your code and make sure you have this Limelight helpers library installed.
Let's see
if you don't, I'll quickly post the link to that.
I can do that. Fine.
Okay, so we have that posted in the chat, but we're going to go back to our code.
Should be April 2.
So first we're going to go into our robot folder. We've got it right here. And we want to create a new folder to store any command classes we're going to be creating. We haven't made any so far, so we don't have that. But usually this is a good practice. So we're going to create the folder commands using this button up here, this folder icon for a new folder. Then in here, we're going to want to create a new file. And we're going to title it aim at April tag command.java. And it's a bit of a long name, but it's descriptive. So here we have our aim at April tag command. The first thing we want to do is extend. And basically, this kind of tells it we're not creating this completely from scratch. We're working off of a base. And we're going to use the command base. And you're just going to want to use the word command here, not command base that is depreciated. So command, just like that. And you're going to need to press tab to import it up here. Then we're going to want to create a constructor for this. So to create a constructor, you use the term public, and then you don't have a return type. You just do the name of the class. So aim at April tag command, parentheses, and we're going to want a drive subsystem as our import. So drive subsystem, and tab to import that as well. And we're just going to call that one drive subsystem. Now we need to save this drive subsystem. So we're going to need to create a little store variable up here. Private would be good for this, but private drive subsystem, because that's the type of our field. And we're just going to leave it like that. And then here, we're going to update its value. So we run this constructor, and right now all it does is it takes the drive subsystem we passed in, and it saves it inside the class for further use. We're also going to want to create a PID controller with the constructor. So PID controller, and then tab to import it, and we're going to call that MPID controller. And if you see that M underscore in front of a variable, all that means is that it is a field of the class, not a local variable. It's not necessary. It's just kind of like using camel case for your variables and like capitalizing the S here. It's just a stylistic choice. But we're going to set PID controller to be equal to a new PID controller. And this is where we're going to be able to set our KP, our KI, and our KD. So we're just going to go very modest right now. We're going to say that our KP is going to be 0.01 because the Limelight returns things in degrees. If we're, say, 30 degrees off, right, if we were to go with 0.1, that would give us a value of 3, which is already a bit fast for our robot, given 1 is the maximum turn speed. So we're going to go with 0.01 just to be safe. And then for KI and KD, we're going to go with 0. Usually, you going with 0 is perfectly fine. Now, one other thing we're going to want to do for our PID controller is set a tolerance. And for now, let's say that 5 degrees, getting within, actually 3. We'll say 3 degrees. We can change this later. Getting within 3 degrees of our target is good enough for us. And also here, if you wanted to set your desired angle to be something that wasn't exactly on the target, but was perhaps a bit off from the target, you could change your set point. We're going to set our set point to be 0. It's 0 by default. That means it's going to be kind of trying to get the set point, or I guess the target, to 0 degrees off. But if you needed an offset, because maybe your shooter's offset, this is a good way to set it. And then finally, add requirements. And we're going to add the drive subsystem, just to make sure that only this command can be using the drive subsystem when it's being run, and to prevent kind of overlap, which can cause issues. So next, we're going to want to add our initialize command. So public, actually, you can do @override first, and then public void initialize. I hope I spelled that right. I did. Public void initialize, and all we're going to want to do during this is reset our PID controller. And as you can see here, all that does is it resets the previous error and the integral term. So if you run the command after you already ran it, you don't have that integral term carryover, which can kind of mess you up a bit. Next, we're going to want to do our execute command. And this is the one that runs every 0.02 seconds. You don't need that command. I'm just including that for clarity. And this is kind of where we're going to put most of the, I guess, logic of the command. So if we don't see a target, we don't want to do anything. We basically just want the robot to stay still. And if we do see a target, we want to use the PID controller to calculate how fast we should move. So this is a perfect opportunity for an if-else statement. So if, and then we're going to be using the Limelight helper. Limelight helper's first result, you can click it, you can tab it, and then dot get fiducial ID. And we're going to be using Limelight as the name of our Limelight. And then we're going to want to check to make sure that that is -1, because this is the case where we don't see an April tag. It's -1 because we're not seeing anything. So in this case, we don't want to do anything. We're going to want to run drive subsystem, mdrive subsystem dot, and then we're going to want to use the method we created on this the other day, specifically maybe not set arcade speeds. Set speeds should work just fine. Or we could, in fact, use set arcade speeds. It kind of makes sense in this use case. But set arcade speeds, then 0 and 0. So no April tag, no motion. Now, on the other hand, if we do see an April tag, this else statement, right? First, we're going to need to calculate a speed that we're going to go at. So let's call that double turning speed. And we're going to calculate this using the PID controller. So M PID controller. And we're going to use this wonderful method. It's called calculate, and it kind of does exactly what you think it would. So you input your measurement. So for that, we're going to be doing basically TX, right? Which we saw how to get back here, limelight helpers.getTX, and then that name. So limelight helpers dot get tx limelight, and it's pretty much just going to calculate how fast we should be turning based on these PID values we set up here when we created the PID controller. So I'll put this onto multiple lines so you guys can see it fully, but that's how you calculate the turning speed. So then if we want to actually set the drive subsystem to turn at this speed, we can do m drive subsystem dot set arcade speed. And then first it takes a forward speed and a turn speed. We don't want to be driving forwards at all right now, but we do want to be turning, so we can just directly pass in that turning speed. Alternatively, if you don't have a set arcade speeds, you could use this right here. So m.drive subsystem set speeds, right? If you have like set tank speeds or something like that, and then you could just do turning speed and negative turning speed. Depending on how your robot is set up, specifically with the tank and where your camera is and how it's oriented, you might need to switch where your negatives are, or you might need to add a negative there. We're going to see that when we put this on the actual robot and see if we need to switch where the negative is. So this, for the most part, is going to be doing that aiming logic. And for now, we're going to add an end method, public void end. And something important about the end method is it takes a Boolean. And we're going to name it interrupted because that is the most logical name for what it actually tells you. But you can name it anything you want. Basically, this will be true if the command is interrupted by another command trying to start. So let's say we're running this, right? We're running this aim command, but then we press another button and it runs another command that needs the drivetrain. Maybe it spins the drivetrain in a 720-degree turn super fast to confuse our opponents. The command would end, and this variable would be true. That's useful if, for some reason, you need to end the command in a different way if it gets interrupted, as opposed to if it ends by itself. And you'll see how it could end by itself soon. But either way, when our command ends, we kind of just want to stop the drivetrain. We already have a default command set for the drive subsystem that just drives using joysticks. So this isn't 100% necessary, but it is good to add an end method on anyway, kind of just in case. So set arcade speeds, and we're just going to do 0, 0 again. Nice and simple. So we're not going to have the command end yet. We'll do that after we test this first part, just to make sure everything's working before we adding is finished. But before we deploy, does anyone have any questions?
I would connect.
Okay, so we have a good point from someone here that we should probably connect to the Limelight first before we deploy. This will be our example of kind of, wait, that's not, of kind of how to connect to a Limelight and configure it. So I'm currently wired to my robot using a USB cable. You can connect via Wi-Fi to do this, but hopefully if I go to 10.25.39.11, and then 5801. Oh, 5801. Hopefully this should pop up as a beautiful Limelight configuration page. I need to plug it in directly to one. Okay, so unfortunately it did not connect. So we're going to be checking our connection real quick. Limelight.local, right?
Maybe, but I don't think the USB can actually get past it. So
So unfortunately, while we're connected to the robot physically via USB-B, it won't actually let us connect to the Limelight at the same time. So we need to do that on a separate computer here. Hopefully you can see.
it's coming from
I think it's just from the screen.
your screen, yeah.
Yes.
Lock that.
So one second. Let me try changing tabs to something a little darker to get rid of that glare. Okay. So here we have our Limelight configuration window, pretty much. Over here we have the what is it called? Sorry, over here we have the vision feed. Sorry, people here. I know you can't see this very well right now. You can like come over and huddle around if you want to see it, because I know it's not streaming to the screen. But we have our vision over here, and we have our configuration settings over here. We're on pipeline 0. If you want to change that without setting it in network tables or via like commands in Java, you press ignore network tables, and you can change which one you're on. We're going to stop ignoring it and just let it stay on 0. You're going to want to go into input, make sure your pipeline type is April tags. That's going to work the best. And then source image camera should work. And we're going to choose 640 by 480, 90 FPS. And LEDs can be off because you don't really need them right now. You don't really need to project light onto the April tag to be able to see it. Room lighting or competition lighting should pretty much be good enough. And we're going to want to turn this exposure down until we can no longer see that little green arrow on our April tags. Usually this is going to be past when you can like stop seeing the April tags, but their algorithms for detecting them are pretty good. So we're going to turn it all the way down. And also we can turn the sensor gain way up to 15. And then we can probably turn our exposure down a little bit more even. So I'm going to keep it around there. That seems pretty good for right now. Now we're going to want to go into configuration. April Tag Classic should work perfectly fine. U Michigan for our engine is good. And for marker size, this is, I think, the normal size of an April tag. Detector downscale. If you set this to 1, it'll run a little slower, but be slightly more accurate at farther distances. If you set it to like 4, it'll run a lot faster, as you can see, but it's going to have a harder time seeing it. As you see there, it's kind of flickering in and out. 2 is a pretty good middle ground for this. Also, if for some reason you wanted to crop your screen, you can use the crop value here to crop the left, right, bottom, and top of your screen. And in advanced, we're just going to keep full 3D targeting off for now. So as you can see, we have our number 8 April tag here. Also here, ID filters. I was trying to find it. It's kind of hard to see this computer, but ID filters, you can enter a comma-separated list of IDs that you want to look at. So for example, if you imagine that 8 was a stray tag that we didn't want to be looking at, maybe that's not the goal. Maybe that's like a trash can that we don't want to be shooting our game pieces into. We could set 1, and then let's maybe say 2 is the other, or 3, I guess. 2 is our other goal. 8, you see it becomes red, and we're no longer tracking anything. Now, we're going to want to basically track any April tag we see right now, so we're going to leave that blank. But if you set it to 8, for example, it keeps 8. So that's pretty much how you calibrate network tables. Sorry, not network tables. That's how you calibrate a Limelight using this Limelight software. If you want to change your team number, that's in settings, and then it's up at the top. And also your IP address, you can change those here and stuff like that. Also, limelight.local 5801.
What if you had two?
That's a good way to get to that. If you have 2 Limelights and you need to change them, you need to change your IP addresses so you don't get collisions. You would change this to something like 12 or 13, usually counting up from 11. And you would also add a little name on the end here. So right now, this one's just called Limelight, but maybe you have a Limelight on your intake and a Limelight on your, I don't know, on your shooter or something like that. You have one on the back, one on the front. You call it Limelight back, and you can call the other one Limelight front. And those are just a few ways to distinguish those.
Don't say, don't say. Figure out if they don't break for me.
We're not going to change any of those because we have the Limelight working right now, and we kind of want to keep it that way for the rest of the presentation.
The new Limelight hardware, Find Your Limelight, works really well. The new one what it does. So if you do lose a Limelight, you can use that to find.
So we're going to switch back around here from looking at that other computer. But we have our code on screen right here. We're going to focus back on this and go up to, actually, deploy wouldn't quite work yet. It would deploy, but we haven't actually bound our command yet. So we're going to go back to our robot container, make a new command, and we're going to call this aim at tag equals new. And we're using this new keyword here, right? Which basically creates a class using its constructor. So new aim at April tag. And we're just going to pass the drive subsystem in there. So notice that new, this creates a new April tag, aim at April tag command. But since it extends command, for type, we can just use command. Now, last time we used a quick turn button to do a quick turn. We're going to repurpose that button just so we don't have to do anything too fancy. We're going to repurpose that as our aim at April tag button. So instead of quick turn, we're just going to do aim at tag. And just as a refresher, mostly for me, our quick turn button is on our right joystick and it's the trigger. So now we're going to try deploying this, and hopefully it builds and successfully deploys to our robot.
strong.
Has it ever worked?
So our code successfully deployed after a minute. So one of the slower deploys, but that's what happens when you have a bunch of new code. So if I get this angled right, we can hopefully see our robot down here. Very cool robot. And we have a little limelight right here, which we have plugged in.
Professionally mounted.
Yeah. So we're just going to turn on the robot, enabling, and as you can see, it doesn't move, which is good because it shouldn't really be doing anything. I'm just going to back it up a little. There you go. 1 second. Let me make sure our joystick's on the right order. Labeling. So I think some of our joysticks might be mismapped right now. So I'm just going to quickly check those to make sure they're all correct. Sorry, guys, it might be a minute or two, but we're just having some technical difficulties. So. So basically, one side of our wheels was just not running at all. We powered off the robot, powered it on again. That fixed it. So we're ready to continue with our presentation. Basically, as you can see here, we have our robot. It's disabled. I'm going to enable it, turn it around so you guys can see that little line right there. So right here, we have our limelight. And also, on my screen, I am able to kind of see what that limelight is seeing. And right now, it's seeing you guys on the computer. So that is wonderful. Now, if I back this up, so we have a little more room over here, it's now able to see the April tag. And basically, if I pull our trigger, it just happens to look at this. It turns towards the April tag, as you can see. So right now, it can't actually see the April tag. It sees nothing. It's a little too far off. But if I get a little closer, we can see the April tag. And when I pull the trigger, it turns towards it. So right now, it is functioning properly. All of our inverts and whatnot worked correctly. And to prove it's not just turning to a certain angle, I can drive it over here, for example, turn it a little closer so it can see it. And as you can see, it turns to that April tag. So you can use that for shooting, for example. Now, if we want to have somebody go take that April tag and walk around with it, we could also show the robot following them around. So that's something pretty cool you can do with this. So we're going to have Anchi here, one of our programming team members, be hunted by the robot. So as you can see, it follows Anchi around, kind of.
Yeah, that's enough.
That's enough.
I'm tired of that. I'm done being hungry.
So So that is basically the lab section for how to get an aim command working. It's really not too complicated, especially with classes like Limelight Helper existing and PID controller that do a lot of the work for you, and this nice command framework. Let me get back to our presentation. So one last thing we're going to do is this kind of optional project. We were going to do this if we had time. We have quite some time left, so I think we can fit it in. But basically, if you have a command, right, or if you have a limelight looking at your April tag, you can tell horizontally what your distance from it is, but you can also tell vertically what your distance from it is, kind of based off of how much off your angle is. So if the April tag's above a certain angle, you know you're really close to it. But if it goes beneath a certain angle, as you can see as I move my camera back, I'm not lowering my hand, but it is a lower angle. So you can use that to kind of determine your distance from an April tag or a piece of retroreflective tape, really any target. So what we can do is we can also use some PID to drive forwards and backwards until the April tag is at a certain height. So then not only do we aim at it, but we also drive to a correct distance from it. And if we do that, we can actually have it follow someone around carrying the April tag, which is a lot of fun. So to do this, we could modify this aim at April tag command. But one of the benefits of making commands in their own files is it's pretty easy to make duplicates of them. So what I'm going to do is I'm going to take this and Control C, Control V, and we're going to get aim at April tag command copy, and I'm going to rename this one to follow April tag command. And it's pretty much going to be very similar to our last one. We're going to call it follow April tag command and follow April tag command here. So we're going to need another PID controller. This one for distance, we're going to call it M distance PID controller. And we're just going to set it to the same values as our original one, because those seem to work out pretty well. That's not a number, is it? There we go. And then our tolerance, we can also go with 3. And a set point of, well, this is one of those cases where we don't actually know quite what the best set point would be.
Controller 20.
What?
20.
Oh, yeah. So these need to be distance controller. And this here specifically, this set point, we're probably going to want to change because we don't quite want the April tag to be exactly in the middle. We want it to be a little higher or lower than middle if we're going based off of distance. And the best way to figure that out is experimentally. So I'm going to go over and quickly check what angle our April tag is if it's at a reasonable distance from our target. So I went into the Limelight dashboard, and it appears that right now the target is about 9 degrees above X. So +9, we're going to set our set point to 9. Now, down here in execute, we have this, which works pretty well, right? We don't want our thing to drive forwards if it doesn't see any tag. And if it does see a tag, we want it to turn properly. But something else we want it to do is if it's within tolerance, right? If it's at a set point for turning, we also want it to drive either forwards or backwards, depending on the height of the tag. So we're going to use another if-else statement for that. So if PID controller, and we're just using our original one there, at set point. And this method here, if at set point, tells you if you're within the tolerance for your command or for your PID controller. So in our case, if we're within 3 degrees left to right. And if we're within tolerance, we're going to want to do M drive subsystem dot set arcade speeds. And we're going to want a new forward speed, so double forward speed. And pretty much just exactly the same as this, except we're going to be using the drive PID controller. It's called distance PID controller. And get TY. So using that, we're going to do forward speed of forward speed and then turning. Else, we're just going to drive like this. So hopefully this should allow our robot not only to just turn to the April tag, but also go to a correct distance for it, which is something that you'd often do when shooting into a goal if you want to always be in the exact same spot for that shot. So we're going to drive our robot over here and deploy this. Our build failed there, so I'm just gonna make sure that this is like extra plugged in and try again. Okay, that time it worked. And only 15 seconds. That's probably a new record. So if we try this out again on our robot over here, I'm gonna drive it around. And we're gonna try that same trigger. So we call the trigger on it, and unfortunately it does not appear to be driving forwards right now. We try again. Still no luck with that drive. So clearly we have an error somewhere in our code or a bug. I guess we need to figure out where that is. So what's that?
Established it.
If you guys have any insights for where the bug might be, let me know. But okay. I think it was Brandon Lowe. Thank you. I think that's not exactly it, but that is the bug. Or at least basically the bug. I just never changed what command it was bound to. So we were running the old command, so of course it didn't drive to the new. It didn't follow the new command. But now it's bound properly, so that's my bad. We'll get that robot back over here and redeploy. So. It did. It gets bound right below. So we're going to deploy again by pressing that W, deploy robot code. Hopefully this time it's really fast. Maybe. 11 seconds is my bet. Darn, 13. But very close. So if we watch our robot again, hopefully this time it's either going to drive towards or away from the target when we activate it. So as we can see there, it does in fact go to a certain distance from the target. Yes. We have some people passing by, so we'll let them move on. The Lego League. But there's our robot. If we enable again, and let's say get a little too close, right? If we pull the trigger, it does back up. So we don't have the P very high for that. So it's kind of got some leeway. But if you say drive over here, and then turn and pull the trigger, we'll turn towards it, and then we'll drive to a certain distance. Now if we had someone run around with it, theoretically the robot should kind of follow it.
Archie, you're up.
And if
Or you could just pull the trigger. Theoretically that would.
right trigger.
Yeah,
I don't know if you want to be there.
do it.
Okay.
You can go to the
I
other
would
side.
need
I
one
wanted to
there.
drive it away, but
That's-
Okay.
Oh, sorry. Yep, pass through. You're all good. I am pulling it.
Like there, and then if I back away, it starts falling.
Can y'all still see this? Yeah. Oh, I keep on losing you,
There you go. There, it's still falling.
and you're
It's a
out
little
of frame.
sketchy, but
You're out of frame now.
you did it.
how am I out of frame?
You're fine.
Just because you can see it there doesn't mean you can see it on the screen.
I didn't realize that's what you meant by out of frame. But anyway, as you can see, it follows me. Pretty cool. Now we have a bunch of robots. And then, of course, if it doesn't see an April tag, it just stops. So. So. That's our demonstration for today. If you guys have any questions, you can ask them now. The code for today should be published in the chat, as far as I know. Yeah, it's basically just the programming workshop GitHub posted by Anchi Paul. I'll just repost it now. But if you go to that and you choose week 3, that should have some example code that works for Spark Maxes, Talon SRXs, and Talon FX. We also have a feedback form, which hopefully was posted. It should be pinned. I'll post it again in case you guys didn't have a chance to look at that. Okay, it was just posted. But if you guys can fill that out, that would be really helpful. Thank you guys for attending. But that's it for today.
There's a question.
Oh, you have a question?
Oh, I'm mute as well.
Yes, Brandon. So if it doesn't see an April tag while the trigger's held, the joysticks will not be able to control the motion. That is correct. If you still wanted the joysticks to be able to control the motion, something you could do is you could pass the joysticks into the command as suppliers, so double suppliers, kind of like let me see this. So like left joystick dot get X or something like that. And then in here, you could add a parameter for double supplier. And then like left joystick. And then instead of using zeros down here, you could replace it with like left joystick dot get as double. But you'd need to save that as like a field. So that's an option to do that if you wanted to. But for now, yes, it would just not move if you held down the trigger and it didn't see a tag. Another option would be to just make the command end immediately if it didn't see enable tag. So the way you do that is you'd make an isFinished method. This returns a Boolean, so isFinished. And then you would do just this right here. So if it's -1, you'd return true. So just returning that would work. And so then if you don't see enable tag, it would return, yes, I'm finished, and the command would just end. And then you'd be able to control it with joysticks. A downside of that is that if you suddenly saw enable tag, you'd need to pull the trigger again. So those are some options. Other than that, just fill out the feedback form if you can. Thank you for attending day 3. Next time we will be going over autos. So have a wonderful night. That's all.
See you Wednesday.
See you Wednesday.